Now back to hypothesis testing. Previously, we used a random simulation to provide a p-value. This works, but there are more efficient ways. Now I'm going to draw on some mathematical probability theory to produce a direct way to test a hypothesis. These techniques tend to differ depending on the type of statistics. So we're going to start with a technique that works only for a statistics which is a difference of proportions. Let's review what's going on with a difference of proportions. I'm going to make this a very specific situation. There are two categorical variables, one which is dependent and one which is explanatory, and each has only two categories. The two categories in the explanatory variable are two different groups, and the study is really about the two groups. They might be two parts of a population, men and women, cats and dogs, spruce trees and pine trees, whatever. There are very often test and control groups. In any case, the point is to determine a difference between the two groups. Then there are two outcomes in the dependent variable. Again, these can be any kinds of pairs, happy or sad, tall or short, healthy or infected, so on. The question is always this: do the two groups have different outcomes? And this is measured in percentages. If the percentage of one outcome versus the other differs between the two groups, the statistic that measures this is the difference of the percentages, the difference in proportions. I've already mentioned it, but this is the standard setup for a controlled trial, one of the most common and most reliable experimental designs. Two groups, one that is neutral and one that is affected by some treatment, and treatment can be very broadly used here. There are two outcomes. Then you determine if the affected group has a different rate of outcome from the control group, the difference in proportions of outcomes. We'll use an example to demonstrate this. The example is a psychology study. This one is a bit old since it's about buying physical media, but work with me here. The subjects were presented with a scenario. There is a DVD of a film that they want to see, and they can purchase it right now for a discounted price of $15. Again, this is an old study, so assume that physical media is the only way to get a copy of this film. They are asked if they would make the purchase. But the psychologists are interested in something called opportunity cost. Buying this DVD means that these subjects will have $15 less for something else. So they split the subjects into two groups, a control group and a treatment group. They asked the control group a simple question: buy the DVD or don't buy the DVD. But they asked the treatment group a different version, where the second option also includes and keep the $15 for other purchases. They wanted to know if this reminder, if making the opportunity cost explicit, would change the behavior of the subjects. They ran this on 150 subjects, 75 control, and 75 treatment. This is a controlled trial, so it is a difference in proportions. What percentage of the control group chose to buy, what percentage of the treatment group chose to buy, and what is the difference in those percentages? Here's the data, presented as a contingency table. More subjects in the control group bought the video, and more in the treatment group, when reminded about the opportunity cost, declined to buy the video. I could also use a standardized bar plot to demonstrate that difference. The sample statistic is the difference in the proportions, treatment minus control. Recall that the hat here indicates something from the sample, not something from the whole population. The numbers from the table are here, and 34 of the treatment group chose not to buy, while 19 of the control group chose not to buy. I'm measuring percentages here of who chose not to buy the DVD. The difference between those two percentages is 0.2. The null hypothesis says that there is no actual difference in the population, and the sample difference is just random noise. The alternative hypothesis says that this reminder of opportunity cost will actually have a general effect in that whole population, and that effect will be to lower the rate of purchase, so that this difference is positive. Previously, we did simulations to determine the p-value of the sample statistic. We could have done the same thing here, assume the null hypothesis, generate random samples of 150 subjects, shuffle the data, make a histogram. This is an example of what such a histogram might have looked like. Our sample statistic is way out at 0.2 past almost all of this data. It is past, in fact, 99.4% of the data, so that the p-value is 0.6%, and that would almost certainly show significance. But I don't want to have to do simulations all the time. Last video I mentioned the central limit theorem. It applies here, and, at least under good experimental design, it should apply to all differences of proportions. What did it say? Well, it applies to sample distributions, data sets where each data point is a statistic for some randomly generated sample. That's exactly what we have here. The count on the axis is how many randomly generated samples that have a certain difference in proportions. Then what did the central limit theorem say? It said that as the number of random samples grows, this distribution becomes more and more like a normal distribution. So I'll use that. Instead of simulating a bunch of samples, if I know from the mathematics that the distribution of samples will eventually just be normal, well, why don't I just directly go there? I won't do any simulations. I'll just let the math tell me that if I did many simulations, then I would get a normal distribution. I've drawn the bell curve through this as well, just to show the standard normal distribution shape. Well, then I can again put the sample statistic 0.02 on this graph and ask how likely it is. And it still seems pretty unlikely. But if I do this mathematically, it would be nice to have a direct way to calculate how unlikely. Well, this is a normal distribution, and from the last video, I have z-scores. Here was the calculation of the z-score from the last video. The unique data point x minus the mean divided by the standard deviation. I want the sample distribution from the null hypothesis, which says that the difference in proportions is 0. So the normal distribution will be centered at 0, so the mean will be 0. I also need to know how to calculate the standard deviation, which I'll get to in a minute. For now, that number in this case is 0.078. Well, then the z-score of my statistic works out to 2.56. It says that my statistic is 2.56 standard deviations away from the mean. Also from the last video, the z-score gave me percentiles. These are from a table, and if I look up 2.56 on the table, I get the 99.48th percentile. This sample statistic is greater than 99.48 of the randomly generated samples. Well, what is the p-value then? The p-value is how unlikely the sample statistic is to be generated out of the null hypothesis. If this sample statistic is above 99.48% of the distribution, well, then there's only a 0.52% chance of generating at least this value. The p-value is just 1 minus the percentile. So here it's 0.0052, or 0.52%. If our threshold of significance is 0.05, well then 0.0052 is much less than 0.05, so the result is certainly statistically significant. That's it. That's the idea. The central limit theorem says that the sampling distribution is normal. That means I can calculate a z-score for my sample statistic, which I can change into a percentile, which I can change into a p-value. Well, wait, what about the standard deviation? I just pulled that number out of thin air on the last slide, but where did it come from? Again, probability theory and some heavy mathematics have figured out how to calculate this. Here's the theory stated quite generally. I'm measuring a difference in proportions for two categories in the explanatory variable, category 1 and category 2. The sample statistic is this difference. Each category has a count, its sample size. Here are those numbers. The central limit theorem, again under certain conditions, says that the sampling distribution will be normal. Its standard deviation is calculated by this strange equation. Lastly, standard deviation in this particular context, that is for a sampling distribution, is also sometimes called standard error. Multiple terms is annoying and confusing, but we are stuck with them. And sometimes this standard error is written SE instead of the more general sigma. All right, that's the theory. Let's calculate for this example. Here is the contingency table again for our two categorical variables. I'll start with the numbers n1 and n2. These are the sample size for the individual categories, and here they are both 75. Then I need the proportions p1 and p2. However, I have to be careful here. I don't want the difference in proportions from the sample. I'm trying to understand the sampling distribution produced by the null hypothesis, since that's how hypothesis testing works. The null hypothesis says that there's no difference between the proportions of the two groups. Well, that means I have to look at the totals here. In these totals, there are 150 cases, and 53 of those declined to buy the DVD. That's what I want to measure. So P1 and P2 will both be 53 divided by 150, which is 0.35. Since this is the proportion of the total, this will be often called the pooled proportion. For the hypothesis, both proportions should be set to the pooled proportion. The null hypothesis says that there is no difference. The mathematical theory is more general and more powerful than we need here. It will give the standard deviation for any kind of hypothesis that sets a specific value for the difference of P1 and P2. Only by remembering that I want the sampling distribution for the null hypothesis do I get the correct use of the formula. Finally, here's that calculation. By the null hypothesis, both proportions are equal to the pooled proportion, which is 0.35. Both categories have 75 subjects, so N1 and N2 are 75, and the result works out to 0.078, which is the number that I used to calculate the Z-score. Let me recap, since there are many steps to this process. You start with a sample statistic, which is a difference in proportions. Then you calculate the pooled proportion, which is the proportion of the total across the two categories of the explanatory variable. Then you calculate the standard error using the pooled proportion for both proportions and using the sample size for the two groups in the explanatory variable. Then you calculate the Z-score of the sample statistic using a mean of 0 and the standard error which you just calculated. Then you take your Z-score to a table to get a percentile. Then you subtract your percentile from 1 to get a p-value. And finally, you use your standard of significance with this p-value to determine whether or not you can reject the null hypothesis. Lots of steps for sure, and lots of vocabulary, but hopefully this is doable, and it is certainly a lot easier than programming and running a whole new large simulation each time you do this.